The topic of today's class of my talk will be this concept called Lagrangian flow, which describes the motion of a little mote of dust being moved around, or advected is the fancy word for it, advected by a fluid, right? So an incompressible fluid, the state of an incompressible fluid at time t in some domain omega is given by its instantaneous velocities at every point of omega, okay? And so the motion of a tiny so-called passive tracer particle, passive means that it's not affecting the motion of the fluid around it. The motion of a passive tracer particle is simply given by integrating along the streamlines of this velocity field. In practice, the velocity field itself, ut, is possibly time dependent, okay? And typically that time evolution is given by one of the typical models of fluid dynamics, for example, the Navier-Stokes equations. It's a dissipative semilinear parabolic problem on the space of velocity fields. But I'll get a little more into that as we go along. If you like, for instance, you could imagine that the u doesn't depend on the t, okay? And so phi t is just the solution to some incompressible ODE. Now, this incompressibility, this this divergence-free condition says that the resulting flow, the resulting Lagrangian flow itself is an incompressible flow. That is, it preserves the Lebesgue volume on omega. And so the phi t's themselves are a flow of volume-preserving diffeomorphisms on omega. And so Lagrangian flow is actually something that you all should be intimately familiar with if you've had a little bit of milk mixed into your cup of coffee or tea earlier this morning and during one of the coffee breaks. Okay, you might have noticed when stirring around the milk in the coffee that you produce this kind of very complicated pattern, these striations and folds of milk in the liquid as you stir it in until pop, it seems to just pop into place and the milk is completely mixed in the fluid, okay? And so really what's going on is that the milk, or in this case this fluorescent dye here, is helping you visualize the motion of the Lagrangian flow, okay? And the complicated structures that you see here, this complicated folding and stretching sort of, is indicating that the Lagrangian flow has some sort of chaotic properties, okay? In the case of mixing milk into coffee, quite chaotic in fact. So the stretching and folding mechanism should be creating some hyperbolicity in the system in exactly the sense of Stefano's talk and Sylvain's talk earlier this morning. A very classical example of this, a time-independent one, in fact, so the u doesn't depend on t. A very classic example is given by the famous ABC flow, if you're familiar. I think I'll be writing it down somewhere in this. Yeah. Maybe the next slide. I would mention, just because this Lagrangian flow is of central importance in the study of fluid mechanics. It's an entire framework for understanding the dynamics of a fluid, and so this little picture here is actually taken from a Nature article from 2008. So when I say chaos, I'm referring specifically to this notion of hyperbolicity that Stefano and Sylvain have been referring to. So here I have sort of a very classical example of a hyperbolic system on the torus, given simply by applying to a vector x this matrix 2, 1, 1, 1. Okay, this is a Safla joint matrix with two eigenvalues, one larger than 1 and one smaller than 1. And so the resulting eigenspaces are stable and unstable directions, respectively, for this diffeomorphism on the torus. Okay, and as you see here, you have a little cat that gets stretched along the unstable directions and contracted along the stable directions. I apologize. The motion of the pointer is extremely chaotic, as it turns out, because I have a sort of natural oscillation frequency myself. So The chaotic features exhibited by this and more broadly by these uniformly hyperbolic systems include, for instance, sensitivity with respect to initial conditions. If you start with two little dust particles and you watch them move around, okay, their position at time n will exponentially separate, okay, after some point, right? So these two could actually come back really close to each other, right? And then go apart. But if P1 and P2 start extremely close to each other, they're separated at an exponential rate. The second sort of chaotic feature is correlation decay. All right, it's the rate at which to some extent, the rate at which the milk mixes in the fluid, right? It's the rate of equilibration to the equilibrium statistics of the system, right? You could also think of this as sort of quantifying the extent to which the random variables psi precompose fn of x are an IID system, right? Of course, for a deterministic system like this, the state at time n depends on the state at time 0, right? But somehow for chaotic systems, memory decays at a relatively fast rate. So these sorts of chaotic features are exhibited by all of these so-called uniformly hyperbolic systems that probably Stefano will be talking about in more detail as we go along. The problem is, though, that even though this stretching and folding mechanism in the Lagrangian flow should be creating hyperbolicity, the hyperbolicity it creates is tainted somehow, okay? It's tainted by a phenomenon known as cone twisting. And unfortunately, I don't have too much time to talk about these sorts of things. So let me at least draw your attention to a sort of toy model of this stretching and folding mechanism. This here, I'm not going to write it down, but this here is a phase portrait of the Chirikov standard map, which is sort of a very famous model of this stretching and folding mechanism in Lagrangian flow and for other phenomena in dynamics. And you see that there's this green region here where, and so maybe I'll point this out. Every single color is a trajectory, okay? So these orange bands here are locked into sort of rotational dynamics where they sort of spin around forever and never leave, okay? Certainly never mix and certainly don't exhibit sensitivity, right? Whereas trajectories initiated in these green regions here, okay, are going all over the place. Are going all over the place. They do exhibit in experiments. They do exhibit sensitivity with respect to initial conditions in the sense of a positive Lyapunov exponent. I'll say that a little bit later. But somehow you think of Lyapunov exponent being positive as measuring the hyperbolicity of the system, right? The trouble is, though, that this hyperbolic region, this green region, this ostensibly hyperbolic region, is very intimately commingled with its opposite, with this sort of elliptic type behavior, okay? And so even when the stretching is really, 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 really strong, it's actually been proved that there's an extremely convoluted commingling of hyperbolic trajectories and its sort of opposite, these elliptic islands. When I say elliptic island, all I mean is an elliptic fixed point satisfying some transversality condition. But at any rate, these two sort of diametrically opposed dynamical regimes sort of are hopelessly intermingled with each other for models of this kind. And so proving, for instance, that a positive area set has hyperbolicity, has a positive Lyapunov exponent, is a wide open question. Okay, it's actually really challenging. Yes?
So just to link with my original diagram, this exactly fits into the category of problem of verifying hyperbolicity.
That's exactly correct.
Taking a system and showing it as hyperbolicity.
That's right, yeah. You would make a quick name for yourself if you managed to prove that this has a positive area ergodic component. That would be a fantastic result. It's referred to as the standard map conjecture. Yes, exactly as you say. So you might ask, when is Lagrangian flow chaotic in the sense of a positive Lyapunov exponent? This question is open even when the dynamics of the velocity field is just stationary, is exactly just the ABC flow, for example. This ABC flow is another example of one of these systems with this sort of convoluted commingling of elliptic and hyperbolic regimes. Okay, and so it seems that in 2019, as has been the situation for the past 30 years or so, to be a wide open question to do anything with this when the velocity field evolves in a sort of purely deterministic way, okay? Let alone when the velocity field evolves according to a real equation, like driven Navier-Stokes. Right? The punchline, however, is that if you allow me to force the fluid with a little bit of stochastic forcing, White in time stochastic forcing, that actually the verification of chaotic regimes for systems like this becomes a tractable problem, okay? I would ask you to consider, for example, the situation where the fluid domain is the 2 torus, okay? And the velocity field evolves according to the Navier-Stokes equation. Maybe I'll just sort of briefly point to the things in this equation, right? This part here, this part on the left-hand side is the so-called Euler equation that describes the motion of an ideal fluid in the absence of viscosity. This little new Laplacian here does the same thing that the heat equation does. It has the effect of kind of smoothing out or mollifying the harshness of the velocity field and making it a little more regular in space. And this part here is a stochastic driving by white noise, colored by some coefficient matrix Q, okay? I don't really want to get too deep into the specifics of the noise itself, but I will tell you the following things, that the noise I consider is always going to be white in time. It's going to be divergence free, and so the left and the right-hand sides of this equation are divergence free. And in particular, the velocity field itself is always divergence free. And lastly, I'm always going to consider that the QWT is spatially Sobolev. You might imagine if I force a PDE by a rough noise that I produce a rough solution, okay, in the sense that it's that the velocity field has poor dependence in X, right? But that's not the case if the forcing is suitably regular, and I'm always going to consider something like this. And so what you get from the 2D Navier-Stokes equations in this setting is a perfectly reasonable, globally well-posed PDE for the velocity field U of t. Okay. In fact, the U of t's can be thought of as trajectories of a Markov process, and they admit a unique stationary measure when the stochastic forcing is sufficiently non-degenerate in a suitable sense. There's been a lot of work in this direction. I'm not going to mention much of it, but probably the most famous paper is Hire and Mattingly from 2006. Anyway, as pertains to Lagrangian flow, when you consider the motion of a test particle at initial condition x naught, this here produces a Markov process on the product space of Sobolev regular vector fields times the 2 torus. Okay. And so under some suitable non-degeneracy condition on the stochastic forcing, we are actually able to show that with probability 1 for all initial velocity, for all initial conditions for the dust particle, and for all initial conditions for the velocity field, that in fact you do get a positive Lyapunov exponent with probability 1 with respect to the forcing that you applied. Okay. This result is also holds by our work for a variety of other fluids models. So I mentioned this 3D hyperviscous Navier-Stokes because you might be wondering if this is special to the situation where the domain is two-dimensional, and it's not. It's not really, okay? The problem with 3D Navier-Stokes, however, is that when you look at 3D Navier-Stokes and you ask, well, does this actually provide me with a time evolution for the velocity fields? Well, that's a wide open question. That's actually one of the millennium problems, right? What hyperviscous means is that in the Navier-Stokes equation, there is a negative Laplacian squared u on the right-hand side. And what this does is it actually ensures that you have a globally well-posed model, okay? So you can think of 3D hyperviscous Navier-Stokes as a kind of cheap way of building a 3D Navier-Stokes that's actually a well-posed equation that gives you anything at all, okay? These other models are are, for instance, 2D and 3D Stokes is the linearization of Navier-Stokes at the origin. So basically you take this quadratic form here and you get rid of it, okay? That's the 2D and the 3D Stokes equations. Galerkin Navier-Stokes refers to finite dimensional projection of the left and right-hand side, okay? So for example, looking at the evolution of, say, the first 17 Fourier modes of the velocity field, okay? I would point out as well that the non-degeneracy needed for this result is actually extremely mild, okay? Already a velocity field given by this sum of 4 shears, okay, on the torus being stochastically driven by these Ornstein-Uhlenbeck solutions. The Lagrangian flow for this velocity field is already producing a positive Lyapunov exponent, okay? Even if you don't believe anything I say about Navier-Stokes. I should mention, in case you're not familiar with this terminology, that the Ornstein-Uhlenbeck trajectories here, these Z's, they're the solutions to this very simple. It's basically the first example of a stochastic differential equation that anybody ever learns, aside from say Brownian motion itself, right? So yeah, here you go. This is Ornstein-Uhlenbeck. I hope I spelled that right. Okay. Oof. Well, for a dynamics conference, that's a lot of stochastics, so please feel free to interrupt me with questions, observations, or angry protest. So, our second result is that, in fact, you not only have a positive Lyapunov exponent, but you also have exponential decay of correlations with respect to the Lebesgue measure. So the milk actually does mix, okay? Assuming that your coffee cup is a periodic box. I'd like to see a coffee cup that the interior, the fluid domain is actually homeomorphic to a torus. That would be fascinating. Anyway, so giving me that at least, what this theorem is saying is that you actually do have exponential correlation decay with respect to Lebesgue measure. Now, the rate is in fact deterministic. With probability 1, you have the same rate, okay? But the constant out front is an inherently stochastic parameter, okay? There are sample paths for the Brownian noise for which that constant could be arbitrarily huge, okay? If, for example, the stochastic forcing is quiescent for 1,000 years, okay? The Navier-Stokes equations themselves relax to 0, and so the velocity field is doing nothing for 1,000 years, okay? So you would expect to wait 1,000 years for your milk to even begin to mix, okay? This constant C here is sort of taking that into account somehow, right? A very quiescent Brownian trajectory is going to result in a very large value of this constant C. On the other hand, though, it's a very low probability event that the Brownian motion is quiescent for 1,000 years, okay? And so at the very least, we have finite moments of this constant C. Actually, we have quite a bit more control in this constant C for a given U0, but time is finite. So. I would mention that just on a very general level, right, correlation decay is a much stronger property than having a positive Lyapunov exponent. For a hyperbolic system, correlation decay is a much stronger property. And in fact, it uses this previous result as a lemma, right? There are lots of examples of systems that admit a positive Lyapunov exponent but aren't exponentially mixing, okay? And Ian Melbourne is giving me this look like, yeah, right, of course. For example, the Pomo-Manvel intermittent map with a neutral fixed point at the origin, or the Buminovich stadium, if you've heard of these models. There's lots of situations with a positive Lyapunov exponent, but no correlation decay. But somehow, under exactly the same conditions as the previous theorem, it actually does work. Okay. I would also draw your attention to the fact that this is something that holds with probability 1. Okay, and so this is sometimes referred to as quenched correlation decay in the random dynamics literature. So this is almost sure with probability 1 exponential mixing. I wanted to briefly come back to the concept of milk mixing in a fluid. because our results have implications for this model called passive scalar advection. So imagine milk is probably a bad example because it's sort of a colloid and milk actually changes the dynamics of the fluid. But you can imagine a very dilute chemical concentration difference, G, right? So if you have a very dilute chemical concentration, this equation here is a very good model for the way that that concentration evolves in time as it's being moved around by the fluid. Okay. On the left-hand side of this equation, there's a partial with respect to t of the scalar g, and then this sort of transport term that's describing the way that the fluid is moving around the scalar, the g, right? On the right-hand side, there's a diffusion term here corresponding to the way that chemical concentrations have a tendency to sort of smear out a little bit, right? This is exactly the same sort of idea as viscosity in the Navier-Stokes equations, where it's sort of smoothing things out. It's a kind of diffusion. And then this last term is a random source, okay? So at every time step, you're adding maybe a little bit of the chemical or taking away some of it, okay? So the relationship with Lagrangian flow is that when there's no diffusion and when there's no random source, the scalar at time t is simply given by this pure advection by the Lagrangian flow. If you're a dynamicist, you would call this the transfer operator of the Lagrangian flow, okay? And so the evolution is given simply by the transfer operator of this thing. And moreover, the gradient at time t is given by applying the spatial gradient of the Lagrangian flow to the gradient of the initial scalar, okay? So if the norms of these matrices are blowing up exponentially as time goes to infinity, then exactly corresponding to that picture we saw earlier of, sorry, I'll just backtrack here. Exactly corresponding to this picture, you see the Lagrangian chaos is the reason why you see these very convoluted folds and striations in the scalar concentration. This picture is exactly saying that the gradient of the scalar concentration is blowing up, okay? And so our theorem has implications for the statistics of the way that these scalar quantities sort of convolute as time progresses, all right? Yes. So, to get a little bit more technical, to get a little bit more precise about how exactly we quantify this convolution of the scalar quantity, we have this sort of analog of the Comingled 4/5 law. It's actually more like the 4/3 law for passive scalar quantities. Okay. What's happening here? Just do a little bit of dimensional analysis with me, okay? This delta LG, right, is the difference between G at x plus L minus G at x, okay? And so if G is a differentiable function, right, then this should scale like some constant times L squared, okay? The velocity field U also is a Sobolev regular, so in particular it's Lipschitz. So the delta LU scales like L times some constant. So on the left-hand side, I have something that scales like this tiny displacement to the third power. But on the right-hand side, I have a quantity that scales like this displacement to the 1 power, okay? And so what this is really saying is that the gradient of G is blowing up as kappa goes to 0, okay? The scalar concentration is getting more and more complicated, is evolving more and more striations and folds, okay? And so this is sort of a quantification, this theorem, which is a corollary of the positively Lyapunov exponent, is a sort of a quantification of this precise scaling law, okay? This quantity epsilon has to do with the relationship. It has something to do with the noise amplitude. Okay. This is another quantification of the rate at which the scalar quantity is convoluting. right? It's saying that the amount of L2 mass of the scalar quantity projected onto the first n Fourier modes scales like log n. But in the interest of time, I think I'm going to limit my discussion of this to just this. I would note, however, that this is sort of to the best of our understanding, this is the first ever rigorous proof of a universal turbulent scaling law for an actual model of fluid mechanics. So this was very exciting to my fluid mechanics friends, my two collaborators. They were trying to do this for a while when in reality they wanted to do some random dynamics. Right. So let me try to put some of the ideas of this proof into context. I come from a smooth dynamics background, so it's perfectly reasonable for me to be here on a conference in smooth ergodic theory. There's a very non-trivial input from dynamical systems, clearly, non-trivial input from dynamical systems in this work. For instance, the multiplicative ergodic theorem, which says that Lyapunov exponents even exist in the first place. This is, of course, Osseladet's theorem that Sylvain talked about this morning. The second sort of primary dynamics input is this Furstenberg criterion for a positive Lyapunov exponent, or many of you might know it as the invariance principle after Avila and Viana. And I will talk in a little bit more detail about these things. But there's also a very highly non-trivial input from stochastic partial differential equations theory. It's quite tricky. It's quite tricky, and it takes a lot of work to make these ideas, these sort of classical ideas from dynamics, mesh with this sort of infinite dimensional setting of a velocity field evolving according to the Navier-Stokes equations. This is a considerable amount of work. That's all I really want to impress on you in this slide. So, the way that, how do you even start? How do you even start with a positive Lyapunov exponent? I just finished telling you, maybe 15 minutes ago, that for this toy model of Lagrangian flow, the Chirikov standard map, that it's an open question to get a positive Lyapunov exponent, right? So what we're going to do is take advantage of some sort of rigidity ideas from dating back to Furstenberg in a very famous 68 paper. So I want you to think of the gradient of Lagrangian flow as a product of a bunch of time one gradients, okay? And since Lagrangian flow is just a diffeomorphism on the two torus, this is a composition of a bunch of 2x2 matrices, okay? Dynamicists are very good at studying compositions of 2x2 matrices. You could imagine a simplified model where instead of depending on the state of the velocity field and the position of the particle, that you just look at a random product of 2x2 matrices where each individual A is sampled from some independent identically distributed law, okay? By the multiplicative ergodic theorem, or you could say this is the Keston formula and so on, that actually predates the multiplicative ergodic theorem, the Lyapunov exponent exists with probability 1, okay? If the matrices themselves have determinant 1, then this number, the Lyapunov exponent, is greater than or equal to 0. It can't be negative, okay? There can't be any sinks if it's volume preserving, right? What Furstenberg proved is that in the case when eta is equal to 0, some sort of disaster has happened, okay? The cocycle itself has a very strong rigid property, okay? There are two cases that Furstenberg picks out. The first is that there is a deterministic inner product that is a product that doesn't depend on any noise or anything. It's just there, here it is, okay? With respect to which these matrices are almost surely isometries, okay? So you could imagine this is corresponding to the scenario when the matrices I'm composing are rotations by some randomly sampled angle theta. Maybe theta is uniformly distributed in some epsilon pillbox, maybe not. It doesn't matter. This is certainly a scenario where you have a 0 Lyapunov exponent. You don't accumulate any vector growth, All right?
Why does it say 1 and not A?
It's IID.
Oh, okay.
So the law is just A1.
It's the same for all.
It's the same for all of them. Stationarity is very important, right? The second possibility, according to Furstenberg, is that there are deterministic lines, the union of which is left invariant by the matrices. And this case is actually, there's a tiny subtlety to this one. It's actually really fascinating. I rather like it. When p equals 1, what this is saying is that there exists a line L with the property that A1 of L equals L almost surely. So an example of a cocycle with this behavior is A1 is given by a random shear in the horizontal direction, where t is distributed according to whatever law you want, okay? Shears have polynomial, at best polynomial gradient growth, at best polynomial matrix growth, okay? That is not compatible with having exponential growth, okay? So clearly, a composition of shears is going to give you a zero-Lyapunov exponent. The case p equals 2, though, is a little bit less obvious, but I like to give this example because I think it's fun. So suppose that with probability 99%, the matrices I'm composing are these very obviously hyperbolic diagonal matrices, okay? I'm expanding along the x direction and by a factor of 2 at each time step, and I'm decaying by a factor of 1/2 in the vertical direction, okay? And so with probability 99%, I sample this matrix. But with probability 1%, I sample a rotation through the origin of 90 degrees. What this does is that my previously expanding direction is now rotated perfectly onto the vertical direction, where it now experiences this exponential decay, all right? And it gets smaller. And so what happens for random compositions of matrices like this is that there's a perfect statistical balance between the growth in the horizontal direction and the decay in the vertical direction. They just get switched, right? They just get switched like this. And so actually this gives you a Lyapunov exponent of 0. The matrices themselves have sub-exponential growth. I think it grows like e to the square root n, something like that. But that's incompatible with a positive Lyapunov exponent, okay? So this is the situation where, in fact, you leave invariant 2 lines, okay?
That second case is also compatible with positive.
It's not incompatible with a positive Lyapunov exponent. That's correct. That's correct, yeah. For instance, I could have just ignored the rotation. I could just compose things like this, and then I leave invariant 2 subspaces, right? Yes, thank you, thank you. So, well, okay, maybe before I go there, let me just say that there is a substantial literature of works expanding on Furstenberg's result in the intervening years to loosen the constraint of IID, let's say, of the matrices that you apply. Okay. In fact, Furstenberg's original result applies to d by d matrices. This is just the 2-dimensional version. It's easier to say. There's a considerable literature on this that's sometimes referred to as a la Furstenberg that has looked into expanding this beyond just the setting of IID matrix cocycles. So for example, the situation when the matrices themselves are depend on the sample of a Markov process, okay? So that would actually fall into this category, all right? Our version of this idea is a version of Furstenberg's criterion that applies when the matrices that you compose depend on the trajectories of a Markov process that's in a possibly infinite dimensional space. Okay, That's really our innovation in this space, okay? And so let me take a moment to sort of talk about this a little bit more coherently. Before, let's just look at the first case A, all right? Before, there was a single deterministic inner product with respect to which I'm almost surely an isometry, okay? Now, it's not just one inner product, it's a whole family of inner products that depend on the state of this Markov process, okay? In the sense that dx phi t applied to the inner product corresponding to that initial condition is equal to the inner product of the sample at time t, okay? When I write star like this, I'm referring to the way that a matrix pushes forward an inner product from one space to another. So this is saying that this Lagrangian flow is an isometry from this inner product space to this inner product space. Okay. And so what's happening here is that on the left and the right hand side of on the left and the right hand side, okay, these inner products only depend on the Markov parameter. Okay. But there might be a whole ton of random paths, okay, different omegas, different distinct omegas, and possibly quite different sample paths for the Brownian motion that get me from exactly this initial condition to exactly this final condition, okay? If there is a broad enough collection of such sample paths, okay, then I can force this gradient, okay, that depends not only on the points x and u, but also on that sample path omega. I can force this gradient to get really, really big, okay? If I make this gradient big enough, that's totally incompatible with being an isometry here, okay? If the initial point and the final point are totally fixed, okay? And so somehow, situations like this where you're in isometry with respect to a deterministic inner product mean that the equations of motion are very rigid, okay? It's a kind of highly degenerate situation that you're in that produces scenario A. It's a very much the same situation in scenario B, where you have these sort of almost surely preserved directions by the Lagrangian flow. You typically expect, in sort of a non-degenerate situation, you typically expect that there's a lot of noise paths, a lot of very different noise paths that bring you from one state to another. There's the pointer. I would mention that there's a very non-trivial input from SPDE theory here that I don't have a lot of time to explain, but maybe I'll say it like this, okay? Solutions to the heat equation is regularizing in the sense that for an initial condition to the heat equation, if you evolve it forward by time 1, it's suddenly analytic, right, smooth. But the heat equation can also be realized by sort of stochastic representation, right? The time t solution of the heat equation for the heat equation on the real line is given by the expectation of the initial condition applied to that point x plus the time t Brownian motion, okay? And so in this sense, we say that Brownian motion is regularizing, okay? Because no matter how rough F0 is, Ft for any positive t is already C infinity. I'll take 1 minute. Oh, I have 5 minutes, that's great. Getting regularization properties like this for stochastic PDE is its own entire industry, okay? A regularization property of this kind is called Strong-Feller. It says that for any bounded measurable initial state, if I evolve forward to time t, it produces a continuous observable, okay? This kind of regularity property is absolutely essential for checking the non-existence of these deterministic families of invariant objects in our criterion. For finite dimensional processes, we're leaning on sort of classical stochastics theory and Hormander's condition. Unfortunately, I don't have enough time to say what that is, but it's a very classical stochastics theory. But in infinite dimensions, we're relying on more sophisticated techniques because this sort of thing is not expected to be true at such a broad level of generality. And for this reason, when we look at the stochastic forcing applied to the velocity field process, we actually need to force infinitely many modes in order to get a regularity property of this kind. Was that 5 minutes plus questions? Or I'm the last one before lunch though, so I don't want to be too bad. Okay. So let me just take 2 minutes to talk about how you get correlation decay. Correlation decay comes from analyzing this so-called two-point motion for the Lagrangian flow that is keeping track of two individual trajectories being advected by the same fluid equations. Okay. And what we desire from two-point motion is a kind of mixing property when you're allowed to average in the stochastic parameter. A property of this kind is sometimes called annealed or averaged correlation decay, all right? And it's easier than deterministic correlation decay or quenched correlation decay because I'm allowed to average in a stochastic parameter. That makes things a lot simpler. And there's a classical theory for these sorts of things. To connect this two-point motion correlation decay to almost sure correlation decay is a kind of L2 trick, all right? Basically what you do is you take this, this correlation function at time n and you square it and you apply Chebyshev's inequality, which produces this, okay? And now I'm looking at the average of observables with respect to this two-point motion, okay? If I have this averaged correlation decay here, then I get an exponentially decaying thing on the right-hand side. And so correlation decay with probability 1 holds by applying Borel-Cantelli to the right-hand side of this, okay? Borel-Cantelli to this sequence of events here. The essential scheme was sort of known to the Sinai school in the early 2000s. In fact, John Mattingly says that he was in that meeting when they were talking about it. But unfortunately, the techniques used in Dolgopia, Koloshin, Korolov don't really work in this PDE setting. So we have to do quite a bit of tweaking and playing around with these sorts of things and sort of building our own stuff. A lot of this is homebrew. So I think I'm going to stop here. Let me just sum this up by saying that deterministic dynamics is hard. Stochastic dynamics is considerably more tractable, at least when it comes to the verification, the rigorous verification of chaotic regimes for dynamical systems. The sort of results that I've talked about here, I would not possibly dream of proving for a fluid model forced by deterministic forcing. But when you do it with stochastic forcing, it's actually possible, okay? And this is sort of my outlook on things, that systems in the real world are inherently noisy, and if you can prove that there's a chaotic regime there for a noisy counterpart to your system, then I think that you've said something very interesting about the system. So, thank you very much for your attention. I'll stop here.